Thanks to everyone for being here. My name is Matteo. I'm a product manager at Move Solutions. And the topic of today's webinar will be our latest release, the new version of the Tiltmeter. First, let me say two things. One, you will receive a recording of this webinar after the webinar. And there will be space for questions at the end of this webinar. So, ask the questions and then they'll be answered at the end. So that being said, yeah, I see the number of participants has been pretty much steady for the past few minutes. So I think that we can start. Yeah, so we're really excited to finally announce the release of this product. The product has been released a few weeks ago, but this is the first webinar where we actually get the chance to tell people what we did and describe the functionalities of this new product. Let me say that this release is really important to us because the Tiltmeter is a device that we have been selling for, it's one of the oldest ones we've had, since 2019. This is the fourth version of the device for us. And I think it's, it's really interesting release in terms of the functionalities that were added and the work that we did to understand what was necessary to improve in a sensor that could be perceived, apparently could be perceived as really easy, as really really simple, a tiltmeter, but but we really wanted to add functionalities to to go in the direction of what our customers have been wanting and they have been needing for the past few years. Okay, let me see. Okay, so first off, let me just describe on a high level some functionalities that this sensor has, but these are functionalities that this device has in common with the previous versions and also with the other sensors of our line. So of course it's a wireless sensor like any other of Move Solutions sensors. It uses a communication protocol which is a low power and long range communication protocol, which is called LoRaWAN. That allows us to reach long distances between the devices and the gateway that is collecting the data. And it's also a low power communication protocol. So it allows us to have really, really long battery life on the device, regardless of how, the sensor is working. So regardless of the settings, regardless of the sampling rate, we can get over 2 years of battery life in pretty much any situation. Another point is that the sensor is integrated into my Move, which is Move Solutions IoT platform. It's not the only option, though. You can also retrieve the data through other systems like APIs or FTP and MQTT connectors. So data is available in many different ways. The sensor can be fully configured remotely through my Move. Installation is easy, and we believe that one of the updates that we did is 100% able to make installation even easier with less constraints. And again, long battery life, as we said, because of a very low power communication protocol. But what's interesting, I would say, is what's new about this device with respect of the previous version. So we worked. I mean, on this device, we're proud of the work we did because we got a lot of feedback from our customers. We went in the direction trying to, on one hand, to add information to the data collected. I mean, of course, it's tiltmeter. Of course, it will detect primarily angles. But there's some other information, as you can see, the peak acceleration measurement that associated with the angles can provide, some interesting information. We'll see how. We worked on adding sampling modes. We used to have on the previous versions, we've always had one single working mode, the programmed acquisitions. Now we've added multiple trigger functionalities to kind of make sure that the sensor is as smart as it can be in detecting the data and picking, the data when it's interesting, and that's where the trigger functionality really steps in and is in, in differentiating between data points that are not worth being collected and actually data points that, because of external factors, because of the triggers, are actually interesting to collect outside of the standard, cadenced and programmed acquisitions. And then there's an access configuration functionalities, which is what I was mentioning before, is making installation easier and with less constraints by being able to kind of reorient this, have a kind of deciding the orientation of the axis for every single one of the sensors, so that you can decide how and in what direction to collect the two angles that the sensor can collect. There's an offline mode in the sense that the sensor is now capable of collecting data when it's offline as well, and I'll describe that later. And then there is add-ons. We're creating add-ons. The first one is what we call the dome, the cover, the protection cover for the antenna for harsh environments. So let's see every single one of them. Let's go a little bit deeper into the description of them. So first, the measures. What the sensor can collect is, well, as always, again, two angles, which we call phi and theta. Alongside that, the sensor, again, as always, can collect temperature. The reason why we've always decided to associate temperature to the two angles, of course, is for correlation. Whenever you see, you're looking primarily at the phi and theta trends. But, sometimes you see certain trends that can only be understood and justified if you look at the correlation with temperature, because of course the structure kind of changes its configuration when the temperature changes. And so correlating that is really important. And that's why in every single one of the event collected, temperature is always present. What we added on this version is the measurement of acceleration, which might sound weird for a static sensor like a tiltmeter. But it's actually extremely interesting because, having an information on how much a structure was vibrating when the data was collected can help correlate, again, certain trends and certain behaviors in the angle trends with maybe a vibrational event. I'm going to give you an example in this one. A typical use case would be if you install tiltmeters on the railways. Well, in that case, if you happen to collect the data right when the train is passing over the sensor, you will definitely have a really strong vibration during the angles collection. Now, the phi and theta are actually not angles collected as like one single data point, but they're always averages over a certain period of time. So the data is collected continuously. When the acquisition comes, the data is collected continuously for a certain amount of time. And then, an averaging is performed. And then, so that data, it's like an average over that period of time. And you can customize that parameter. It can be 1 second, it can be up to 16 seconds of averaging time. You can do that, you can configure that through my Move. But anyways, the point is that if there is something that is making the structure vibrate while the sensor is collecting those angles, well, definitely that might cause a spike in the trend of the angle when then you go later and you look at the data. So having information on the level of vibration on the structure during the data collection, during the angles collection, it's extremely interesting to kind of like identify the nature of that spike. So that's why adding that information is extremely interesting. You can see here what it would look like, like say that those about 7 seconds is the time that it takes for the sensor, to collect the data, and then it's actually the averaging time for the calculation of the two angles. So the acceleration is collected, over that entire period, and the peak value of the acceleration is also identified, and it's associated with the phi and the theta and the temperature, of course, and then it's transferred to my Move, to the platform. So you can always associate that peak acceleration value to the angle values that were collected in that acquisition. Actually, there is another parameter as well, which is called RMS, which it's kind of an equivalent of the acceleration peak. It responds of different needs. It's a little bit of a different parameter, but it goes in the same direction. So adding vibrational data to the acquisition is really important to identify outliers and false alarms. The second point, I think, is the sampling mode. This is probably one of the most important updates that we did. So the idea was, before, again, we used to have one single acquisition mode, which what we called standard cadence or programmed acquisitions. It means that you can set a cadence, and the sensor at that cadence, at that sampling rate, at that frequency, would just wake up, provide an acquisition, kind of go back to sleep until the next sampling comes. And of course, that sampling rate would be decided by the customer. So what would happen all the time is that the customer would end up selecting a really, really frequent, really fast sampling rate, even if maybe it was not necessary. Because of course, if there is an event in between two programmed acquisition, you would have to wait until the next acquisition to be able to identify or to be able to maybe to trigger an alarm. So in order to be as fast as possible in the response, you would have to have like the fastest possible cadence on the sensor, and that's extremely inefficient. You have a bunch of data that is sent to the platform, a lot of data points that are actually pretty much useless, and also the battery life of the sensor is not optimized because the sensor could last a lot longer if it could have a lower cadence. So that's why we decided to add multiple trigger modes. That goes in the direction of, again, trying to make the sensor more smart in identifying different types of triggers, which will be, which are based on different parameters. So there's basically 3 different trigger modes that can work alongside, each one of them can work alongside the standard cadence mode. The first one is based on acceleration. The second one is based on the value itself of the angles detected, and the third one is based on the velocity, the velocity of the angle variation. Again, the standard cadence, we just talked about that. You set a cadence and the sensor would just wake up, collect the data, go back to sleep at that specific cadence. What we did on this one as well, because before with the previous version, we could only go down to 2 minutes. Now we can also collect the data at once every 30 seconds or once every minute. So I think that's important as well to anyways try to provide faster sampling options. But again, standard it has always been there, nothing new. So what's new is, for example, this first trigger mode. It's based on acceleration. So we've described the importance of accelerations for us, to be associated with even static angles acquisition. But this is a little bit different. What you can do here, you can set a threshold in terms of acceleration. And whenever that threshold is surpassed, the sensor will basically provide an acquisition. So that acceleration is constantly monitored. So even in between two programmed acquisition, the sensor will still monitor acceleration and monitor for threshold surpassings. What's interesting also is that the acquisition is not provided right after the acceleration trigger, but the sensor will just wait a little bit. And it will do that because what we want to do is to provide an acquisition that is after the vehicle, whatever it is that is actually making the structure vibrate, is is not under structure anymore. So we don't want to provide an acquisition while the structure is under stress. Because that's not what we want to outline. We want to outline how the static configuration of the structure has changed after a trigger event, in terms after like a strong vibration that triggered the acquisition. So on a practical level, what the sensor will do, the sensor will, when the threshold is surpassed, the sensor will wait and will provide the acquisition when the acceleration is below the activation threshold for at least a time period of 3 seconds. So we'll wait those 3 seconds because the sensor wants to make sure that for at least 3 seconds the acceleration is not surpassing that threshold anymore. Of course it's a waveform, so it will surpass the threshold for a certain amount of time. Will surpass the threshold multiple times, but then it will go back below. It will be steady below the threshold again once the structure is not under stress anymore, and that's when we provide the acquisition. So it's a static configuration of the structure after whatever it was that triggered the acquisition is gone. Another one, a use case here is extremely useful. I'm going to use the same one that I used before, the tracks. So again, you have a tiltmeter installed on railway tracks. You have the train. So say it's a really, really heavy train that is causing a really big vibration. So you don't want to collect the data while the train is passing over the sensor. So the sensor will wait until the vehicle is gone to collect the data. That would be the use case. The second trigger mode is based on it's based on the angle, on the angles itself. So what you can do is that you can set a threshold. The threshold can be set on again, the sensor collects 2 angles, phi and theta. So the threshold can be set just on one of the 2 or on the both of them. And you have full customization options. You can set different thresholds on different angles. And the threshold is not like a straight threshold. It's actually a range of acceptability for the data. Outside of that range, it has a lower bound and an upper bound. Outside of that range, the acquisition is triggered. Actually, so whenever that threshold is surpassed, it's not really about providing the acquisition when the threshold is surpassed. Here, there's a step forward. The user can set a post-trigger cadence, and after that threshold is surpassed, the sensor will change its cadence and it will start sampling at the post-trigger cadence that the user can set. So the user can set the pre-trigger cadence, which is a standard cadence, and the post-trigger cadence. It makes the user have full 100% full flexibility on how to set those 2 cadences. I would say the most common use case would be to have a lower standard cadence, maybe once every 6 hours, and then to have a really fast post-angle trigger cadence, maybe at one sampling every 30 seconds, the maximum cadence that you can have. So the idea behind this functionality is to kind of oversample the angle trend when the angle trend surpasses. So when it is outside a certain range that is it's called the safe range. Outside of that, you want to have a higher sampling rate. Inside of that, you want to have a lower sampling rate because you're not interested that much in the data when it's inside of that range. Of course, then the data that has surpassed the activation threshold, as soon as it goes back down, within the range, at that point, the sensor goes back on its original cadence, the standard cadence. The next one, this one is the last one. It's a little bit more exotic. So the trigger here is based on the rate of change in the angles. So how it works is basically that, say you have a structure and your trigger will be, a certain number of degrees of movement in a certain amount of time. So you can say, I want to have an acquisition if the structure rotates more than three degrees in a 1 hour period. So what happens is that the sensor will continuously monitor for, for that, change rate parameter. And as soon as that surpasses on both angles or just one of them, you can set that through my move. But whenever that threshold is surpassed, the acquisition is collected. The idea here is oversampling basically the angle trend whenever there is a change rate that is fast, and it's kind of downsampling it when the data is steady and it's not changing. So it's like a flat line where right there, if you pick this trigger functionality, when the line is flat, it's going to be downsample because you're probably not interested in a trend that is not changing. So if the angles are not changing at all, you can have like a standard maybe once every 12 hours cadence. But then as soon as it starts changing fast and the velocity is the trigger, at that point you get more acquisitions. Okay, so let's move forward to the next functionality. Here it's a remote access configuration. This is, again, something that changes the way that the sensor can be used a lot. The idea is that before, with the previous versions, you would have one single installation position. So you would have to, be extremely careful with the installation. You would have to install the sensor one specific position. And, if the sensor was with the x-axis pointing up, if the sensor happened to be, for any reason, by mistake, because of installation constraints, if it was installed in a different position, the only option would be to just go there and move it, and so you would have to go back on site and reinstall the sensor in the right position. So we wanted to, our customers, the feedback that it came from our customers is that it would be nice to have an option to kind of rearrange the position of the axis so that the sensor can still work, and you don't actually need to go and change its position. So that's what we did. So let me describe how it works. So these are the three axes of the sensor. There's X, Y, and Z. Of course, the tiltmeter is contains a triaxial accelerometer, and then it provides the two angles, right? So these are the three axes, X, Y, and Z. So this is the default installation position with the X axis pointing up in a vertical direction, and with the y-axis labeled as longitudinal axis and the z-axis labeled as transversal axis, right? So this is the default position. Then the angles detected by the sensors, which are two, are always the rotation around the longitudinal axis, which you can see in the default position is the y-axis, and then and that's phi, and then there's theta, which is the rotation around the transversal axis, which happens to be in the default position Z, right? So what you can do with this is that, and I'm going to show you an example here. This is a structure. As you can see, there is a bunch of sensors. In particular, there's these two sensors that have been installed in different positions. So, well, the x-axis is I mean, it's in the same. Actually, it's in the same direction. So for the both of them, it's vertical. But as you can see, the one on the top of the page, this one is in a certain position, and the other one is 90 degrees rotated, right? So it means that if you don't do anything to it, so if you don't change the configuration in any way, what happens is that you basically detect the sensor will still detect phi and theta, but for every single one of those sensors, phi will be in a different direction with respect of the other sensor, and the same for theta. So when you think about, I want to know, for example, the rotation, what we could call the roll angle of the structure. Well, on this sensor here, you will have to look at one angle. On this other sensor, you would have to look at the other angle because the sensors are in two different positions. So the options, the new option that you have here, and that we have added, you have the possibility to kind of rearrange the axis. So you can change the association between the longitudinal, the transversal, the vertical. So for this one, you can say, well, because this one is actually installed according to the default position. There is the y-axis is longitudinal, how it is supposed to be. This one has actually the z-axis that can be labeled as longitudinal. Well, if you do that, so if you change how those axes are labeled, so the association between, the longitudinal, transversal, vertical axis system and the sensor's axis system, if you change it in that way, what you get is that you detect phi and theta in the exact same way, regardless of how the sensors are installed. But phi and theta are, they have the same meaning, of course, in different points because they're collected in different positions, but they have the same physical meaning for the structure. In this case, again, if we want to give the angles a name that makes sense for the entire structure, for both angles, phi will be the roll angle of the structure, and theta would be the pitch angle of the structure, right? So that's what we did. We provided a tool that you don't have to use. The sensor doesn't need that configuration step to work, but it goes in the direction of providing an additional option to kind of unify the data collection and give every single one of those sensor and every angle collected the same meaning for the entire structure. So let's move forward. Offline mode. It's interesting because one of the things that our customers have always told us is that what if the gateway goes offline? What do we do? Do we lose the data? Well, that's why we added this functionality. There's a flash memory inside of the sensor that can hold up to 10,000 data points. And what happens here is that you can activate a functionality that allows the sensor to keep working and keep collecting data, even if the gateway goes offline. So the sensor itself will go offline, but it will still collecting the data for up to a week. So it gives you time to arrange like an inspection, whatever is the reason, the solar panels are not working anymore for the gateway, whatever it is the reason. It gives you time to to go on site and fix the problem. And the data will be collected, will be saved on the sensor's internal flash memory. And then, as you can see, we added a connector here, so you can go and you can download the data. So it's kind of like a black box. The data is not lost. That's the point. Not only that, you can also, even if, regardless of whether or not the sensor works offline, you can also activate a functionality that allows the sensor to just save everything it collects, whether it's offline or online. Every single data point collected will be saved on the internal flash memory until it's full. And then when it's full, but we're talking about 10,000 data points, it's a lot. It's a lot of acquisitions. When it's full, the oldest acquisition will be overwritten by the new ones. And then the add-ons. So the first one that we have here is what we call the dome. It's basically a plastic protection cap that goes over the antenna. Of course, the antenna, so this is the version of the sensor without the dome, with the longer antenna. And then if you need the version that has also the protection cover, there is a short version of the antenna that fits inside of the dome. That goes in the direction of making the sensor more reliable in certain environments. I'm thinking about rail, where the sensor is exposed to the weather and to high vibrations, and also to vehicles possibly hitting the sensor. But not only that, even in construction sites, for example, a lot of times we've been told that the sensor gets damaged by debris. So it was really important for us to give an option to our customers in that direction. that's pretty much it in terms of, the description of what's new with this version. Now, I just wanted to mention a couple of applications where this new version could really make the difference with respect to previous versions, or with respect of, competitors that don't have those functionalities. So the railway, for example, for the railway, we actually have a tool on my Move. We can calculate the typical, railway parameters, which is the cant, the twist, and the vertical deflection really, really quickly. The cant is the rotation of the tie. If you install a tiltmeter on a tie, the cant would be the rotation of the tie. The twist would be kind of like the torsion of the tracks. So you need two tiltmeters and install a different section along the tracks to calculate the cant. Here it is. The twist, I'm sorry. And then there is the vertical deflection, the vertical settlement. It's basically the vertical displacement of the tracks, and it's detected by installing what we call tilt beams. So it's basically metal beams connected to one another, and with the tiltmeter on top of it, of every single one of them. So as you can see, we can get like a deformation, like a deformation that reproduces the actual deformation of the tracks. So the new sensor, I'm thinking of, the improved, frequency rate. So the improved cadence up to 30 seconds that can really help in being faster with, detecting angles. So that's one thing. But I would say the trigger option, especially, we said that before, the acceleration based trigger, I think it's extremely interesting in this application, because you can set a trigger, and then when the train passes over, right after the train passage, then you can collect the data and see if that train that maybe was heavier than the average, so it caused vibration that surpassed the threshold. Well, if that train caused a static permanent deformation in the tracks. Another application would be the static deflection in bridges. I mean, that can be performed in a couple of different ways. It can be a long-term monitoring, so you can install a bunch of tiltmeter on your deck, and you can monitor long-term the deflection through a specific tool that, again, we can provide, that it's on the platform. That tool will basically, using 4 to 6 tiltmeters installed along the bridge deck, it can calculate the deflection using the angles provided by every single one of those tiltmeters. So you can basically kind of like draw a line that is the actual static deflection of that bridge. It makes even more sense for static load tests, where where you can put really heavy vehicles on the bridge, and you can cause a static, almost visible deformation, and the sensor would pick up that deformation and would provide a displacement, maximum displacement, for static load testing. Here again, having a higher sample rate, so going down to one acquisition every 30 seconds, allows you to be a lot faster in collecting the data. If you're doing like a load testing campaign, and you have to be as fast as possible, with maybe you have to do 4 acquisitions. Well, in 2 minutes you can collect 4 acquisitions. Construction site retaining wall stability. Here, the triggers that we've added are extremely valuable. I think, because when you're monitoring a retaining wall, you're definitely looking for movement in many different ways, right? Especially, so you can have it like a trigger mode that works on the angles themselves. But I think even more importantly, to have like the earliest detection you can possibly have in this scenario, you can have a trigger that works on the velocity, so on the angle's change rate, so that as soon as the retaining wall that used to be perfectly steady starts moving in a certain direction, starts accelerating, you can immediately trigger an acquisition, because maybe your standard cadence was, 15 minutes or 20 minutes or 12 hours, even up to 12 hours, but that you're not missing any data because the sensor is constantly listening for that change, and fast actually change in the in the position of the wall. So I think that would fit really, really well, that application. Yeah, that's it. I'm gonna look at questions at this point. Okay. Okay, so is it possible to have more than one of the trigger modes active at the same time? No, the sensor always allows the standard cadence plus one of the trigger modes. Okay, let's see down here. You can kind of sign up for a demo of the MyVoom platform. We will send you a demo access. Yeah, right after this webinar, we'll send you the login information for our demo access. Thank you. Okay. Okay. Is there any way to retrieve the offline data remotely? Right now, the only way is to actually go on site and connect and collect the data. We're actually working on, trying to find a way to, send that data afterwards, to the cloud. It's not the easiest thing because again, we're using a LoRaWAN communication protocol, which is low power. So it's not high speed. So sending like a queue of acquisition, it's not the easiest. But like it's really like it's really important to have this this functionality also for those like reliability problems that wireless sensor might have, like a wireless system might have. So it goes in that direction first to solve that problem. The housing is made from aluminum. Yes. And the cover is made of plastic. It's a really, I mean, it's a really thick plastic. So it's I mean, the whole sensor will break before the plastic cover breaks. Um, The beams, okay, so it says, are the beams available in 1 meter intervals? If you mean the beams for the tilt beams, yes. The standard option are, I think, 1, 2, and 3 meters long, but then it's possible to customize. It's possible to customize the length as well for specific projects. Does the smaller antenna and the cover impact the communication with the gateways? Not really. I mean, we've been testing it. And I have to say that, for this type of device that it's sending just a little bit of data, at the end of the day, it's static data, so it's just single data points. It basically doesn't change much. Actually doesn't change at all. It doesn't affect the acquisition. Um, okay, let me see if there's any other questions. Answer them all. Um, okay, here it's okay. I don't see any other question. If you had other questions, you can send us an email, info at movesolutions.it. I don't think I have any questions that I didn't answer, but in case there was questions that I did not answer, we will answer them privately. We'll send you an email. Okay, so that's pretty much it. And thanks to everyone. See you in the next webinar.